Morning to you if it's early morning. We are live once again. Baji is enjoying some catnip and currently he's a little bit high. So he's over there. I'm sitting over here ready for lap time because generally at this hour we well we he's usually on my lap and I'm usually reading from the book. But currently he is, oh wow, his foot is on my, hi, hi Yash. Baji just got a little bit of catnip and so he is quite enjoying himself. They all got a little bit of catnip, but it does not seem to have any effect much on Suji. Baji, on the other hand, is rolling around and he is quite catnipped out. Baji! And he is rolling on the counter. How are you guys? We're good. We have been going live kind of late here. We will be doing our usual live tomorrow as well, Saturday and Sunday afternoon, like we normally do. Baji, Korana Shona? Baji? Baji! So, you know, we have been reading from this book called Einstein's Cosmos, that's right here. And I was going to continue some of this reading. We left off at chapter 2 yesterday, and I thought that we'll get into chapter 3 today. And I was hoping that Baji would come and sit on my lap, but currently he's busy with his catnip pursuits and being a little bit too happy about it. And indeed, he is hi, Baji. He's a little high. So I wanted to also share the live on my channel. That's why I forgot to do that. And I have my other device here. So let me do that. But yes, indeed, we are live. And we hope that many of you will join. And that I will see you here, or I'll see you tomorrow afternoon, Sunday afternoon. We have all these different live streams that are planned. So, hi Baji. I will see you here. There's my live on the other device. Your cats are so cute. Thank you, Cam Speeds. Thank you so much. Here is Baji. He just got some catnip. Oh wow, there is some drama going on over there. Suji and Fuji are playing. Actually, they are quite excitable at this time because they just got some catnip. And Baji was rolling on this countertop just a minute ago. And Suji and Fuji are playing. They are sort of chasing each other, and Suji is very energetic. Now she's often energetic, so that's not really too surprising. They might get a bout of zoomies, but can I be moderator before everyone joins? For sure. Here, I'll make you a moderator. There you go. There you go. Thank you. Thank you so much. Cam Speeds is moderator at this time. Hello, I'm here. Hi, not your average cat. Hi. So we've met some people. I think Just a Bean is also a moderator, actually. So Yash, you're also a moderator. If you want to. Desi Food by English Cook. How are you? How are you? Thank you for the emojis. Thank you everybody for joining. We just shared the live onto my I just shared it onto my community tab, so hopefully people can see that we went live. And I was just telling the others that indeed, after this catnip, what I was hoping for is, do you know how to add people into the stream? I don't think I know how to add people into the stream. I just know how to share the live so people know that they can join. Anyways, I think I shared it. It's on the tab so people can see. And then generally people just join when they join. But yeah, oh okay. Yes. Yeah, I shared the live. I don't think I do anything else, right? I just do my thing and then people join. So, anywho, I had settled pretty much on the couch. It's quite late here in Boston, but I've been doing these late night readings for people, and we've had some good discussions about physics topics. And generally speaking, a kitty cat has been sitting on my lap throughout the reading, and it's been quite cozy. Indeed. I won't stay for long because I will have to go. That's okay. That's okay, Yash. That's all right. I'll see you tomorrow. I'll do my usual live in the afternoon sunshine time tomorrow and Sunday as well. Usually it's nice lighting during the afternoon here. So usually that's when we go live and it's nice. But these late night lives have been nice too. So we're just kind of giving it a go. Over here is Swatchy being very playful. So how nice. What a nice view, Swatchy. Thank you so much. Thank you so very much. And we were in chapter 2 of Einstein's Cosmos. Now, usually during these lives, we chit-chat, we hang out, we have the kitty cats, we also read from a book. I also get to like all of your comments and I read all your chat messages in between the reading. And it's generally a lively discussion and a lively chat during these live streams. And sometimes we get to see a lot of action here as well from these kitty cats. Hi, Suji Mama. She is, I think, chasing her tail at this time. Lovely pursuit. Baji's being... This is Suji, actually. Baji is not hyper. He is over there being quite... what's that word that became famous? Demure. Baji is over there being demure. This is, in fact, Suji. Suji is anything but demure. She's a huntress, and she is currently chasing her tail, because why not? You must get exercise somehow in life. So, I love your cat's names. Thank you. Thank you, thank you. Cat is crazy, says Southie. Not your average cat is laughing and also saying, I love your cat's names. Thank you so very much. Really appreciate your kind comments. Oh, wow, you found your tail, Suji. Wow. Hi, Mama, you found your tail. Oh, such a big achievement, baby. My babu. Tumi Shona. Tumi Shona to. Shona Mama has found her tail after chasing for a while. Okay, so thank you so much, everybody, for being here. Like the live, if you will, and we will get started with the book. And we will see which cat joins us here on the lap as we do so. So we have been having a healthy discussion about Einstein, and given his cultural importance as well as importance of his contributions to physics, and given that it's kind of interesting as well as important to understand some of these concepts and how they developed historically, I thought it would be nice to read from this book as our discussion source. Well, not our discussion source, but as our reference, Einstein's Cosmos by Michio Kaku. And we have been reading from this book. And in fact, we are on page 31 of it, chapter 2. But we will soon finish chapter 2 and go into chapter 3, which is Special Relativity and the Miracle Year. So now I've been talking about how Fuji, no Fuji, let's not do that. Fuji, oh come Baji. Baji's ready for lap time. Fuji, no Fuji. 1 second, sorry. Oh, sorry, I thought that was Baji. Fuji, no. No, bacha. Okay, I might have to change the position of this feeder because Fuji's going to end up breaking it. 1 moment, please. No Fuji. No Fuji. Let's not do that. No Fuji. I can give you a little bit of a snack, but please don't keep on pushing the auto feeder. It's very fragile, the wiring of it. So I'm worried that he's gonna break it. Oh God. Anywho, so back to this discussion. They've got their snack now, so hopefully they'll calm down. Especially one of them who keeps on attacking the auto feeder. So basically, in this part, we have been learning more about Einstein's life. So it is interesting to see that Einstein actually faced with a lot of resistance and sort of these obstacles in his early career. And indeed, he was having trouble landing an assistantship or being in the program that would give him his PhD. And eventually to become a professor, he had some obstacles. He even had to change countries and citizenship. We saw how he got more success in Switzerland and became Swiss citizen and had to renounce his German citizenship. But even afterwards, he was having some troubles. And we saw that, he did get into the Polytechnique in Switzerland. But after that, he had been hoping to get an assistantship, but he did not get that assistantship. And then eventually his friend helped him to get a job at the patent office. So that's where we sort of were when we left off last night. Hi, Velikika, what is happening today? So we are chilling and hanging out with some kitty cats and reading from the book Einstein's Cosmos. And thank you so much for joining, and we'll keep going. So, to raise some extra money, he put an ad in the local newspaper offering private lessons in mathematics and physics. So this is Einstein who has to raise some extra money. This is still when he's working at the patent office and he's having difficulty with finances. It was the first recorded mention of Einstein's name in any newspaper. So this is sort of saying that Einstein went on to become very popular and famous. He was often written about. But, the first time he appeared in the newspapers was when he was actually putting in an ad to look for work. So Maurice Solovine, a Jewish Romanian student of philosophy, was the first student to answer the ad. To his delight, Einstein followed that Solovine was an excellent sounding board for his many ideas about space, time, and light. To prevent himself from becoming dangerously isolated from the main currents In physics, he hit upon the idea of forming an informal study group, which Einstein mockingly called the Olympian Academy, to debate the great issues of the day. So this kind of highlights the fact that sometimes, even when you're not formally in science or doing research, or maybe in a reputed research academy, still it's important to keep in touch, and it's important to kind of stay fluent with the topics. And for that, he formed a study group. This is actually extremely important, and very much what happens in universities. It offers an environment for such study groups, but he basically formed one by himself, even without being part of a university at that time. Please have one of the cats read a paragraph. Very nice, thank you. In hindsight, the days spent with the Academy group were perhaps the most joyous in Einstein's life. Decades later, tears would come to his eyes when he recalled the vibrant, audacious claims they made as they voraciously devoured all the major scientific works of the day. Their spirited debates and raucous discussions filled the coffee houses and beer halls of Zurich, and anything seemed possible. They would fondly swear, these words of Epicurus applied to us, what a beautiful thing joyous poverty is. So they were poor, but they had each other, and they had this study group. In particular, they pored over the controversial work of Ernst Mach, a Viennese physicist and philosopher who was something of a gadfly, challenging any physicist who spoke of things that were beyond our senses. Mach spelled out his theories in an influential book, The Science of Mechanics. He challenged the idea of atoms, which he thought were hopelessly beyond the realm of measurement. What most riveted Einstein's attention, however, was Mach's scathing criticism of the ether and absolute motion. To Mach, the imposing edifice of Newtonian mechanics was based on sand, as the concepts of absolute space and absolute time could never be measured. He believed relative motions could be measured, but absolute motions could not. No one had ever... Oh, hi, Baji. Baji's on lap now. Where am I? No one had ever found the mystical absolute reference frame that could determine the motion of the planets and the stars, and no one had ever found even the slightest experimental evidence for the ether either. So, this is when basically Newtonian mechanics and Maxwell's equations are sort of in contradiction to each other. We understand now about electric and magnetic fields with Maxwell's equations, giving a description of them and how that makes light. But people also know about light in general for millennia, and they're having trouble with this concept of light. For example, how do the light from stars travel to us? If light is a wave, does it need a medium with which to travel, such as sound would need? And that led to concepts such as ether. And people were kind of trying to resolve all these contradictory concepts, and whether ether was real or not was still up as a question. And I'm guessing at that time, so Einstein was not really working directly in academia at this time, but he can still follow what is happening in academia, what is being published with his study group especially. And this is actually extremely important for us to note as well, because even if you're not doing research, quote unquote, in a university, you can still follow it and learn from it and see what is being written and see what you think about it, and maybe you can base something off of that. Like that would be those would all be your literature review for your original work. Hi BJ, hi Adventure Life Nova, hi Big Chunga, Baji, I'm BJ, haha. Yes, indeed. Hello, welcome. Thank you for being here. So this is actually very interesting and very inspiring in the sense that he was following all of this work. Not all of the work that is written, that is published as research is of course correct, but it can still help you. Maybe he took inspiration from this absolute motion or relative motion debate. Maybe he took inspiration even from ether. Even learning about something, that is contradictory, or maybe you prove that wrong, well, it still gives you something to to work with, and that's what's important. So one series of experiments that indicated a fatal weakness in this Newtonian picture had been performed in 1887 by Albert Michelson and Edward Morley, who had set out to give the best possible measurement of the properties of this invisible ether. They reasoned that the earth moves. Oh, Baji is making biscuits. That the earth moves within this sea of ether, creating an ether wind, and hence the speed of light should change depending on the direction the earth took. So, after it's been hundreds of years, I mean, this is all happening in, I guess, early 20th century, all this debate about ether. Now we know that there is no ether. But before we knew this, you can imagine that a lot of debate was happening with this topic. Now we can laugh about it now, saying that, oh my God, these people were so silly, thinking about ether. But at that time, they didn't know any better, So it is interesting to know and see the progress of science and see that, you can be wrong about something, and that's still fine, because that still helps to progress science. Because if the assumption was that there is something like ether, yes, he does understand Einstein. If the assumption was that there is something like ether, well, then it should be consistent with other things, such as what this person is saying, which is what about the ether wind? Speed of light should be changing depending on the direction that the earth took. It's basically taking everything else that they knew and had measured and trying to resolve it with what was being proposed. And that's why measurement is so important. Experiments are so important. Think, for example, of running with the wind. If you run in the same direction as the wind, then you feel yourself being pushed along with the wind. With the wind at your back, you travel at a faster speed. And in fact, your speed has been increased by the speed of the wind. If you run into the wind, then you slow down. Your speed is now decreased by the speed of the wind. Similarly, if you run sideways... Oh, Baji. Baby. Now, baby. Sorry. Similarly, if you run sideways 90 degrees to the wind, you are blown off to the side with yet another speed. The point is that your speed changes depending on which direction you run with respect to the wind. So they were thinking about all this. Michelson and Morley devised a clever experiment whereby a single beam of light is split into two distinct beams, each shot in different directions at right angles to each other. Mirrors reflected the beams back to the source, and then the two beams were allowed to mix and interfere with each other. The whole apparatus was carefully placed on a bed of liquid mercury so that it could rotate freely, and it was so delicate that it easily picked up the motion of passing horse carriages. So they came up with a very clever setup to do this. According to the ether theory, the two beams should travel at different speeds. One beam, for example, would move along the direction of the Earth's motion in the ether, and the other beam would move at 90 degrees to the ether wind. Thus, when they return back to the source, they should be out of phase with each other. Ooh. Hi, Molly love. Hi there. Hi, Molly. How are you? So they came up with this whole setup to cleverly measure if there's going to be a difference in the speed of light with respect, because of the ether. Much to their astonishment, Michelson and Morley found that the speed of light was identical for all light beams, no matter in which direction the apparatus pointed. This was deeply disturbing, for it meant that there was no ether wind at all, and the speed of light never changed, even as they rotated their apparatus in all directions. This left physicists with two equally unpleasant choices. One was that the Earth might be perfectly stationary with respect to the ether. This choice seemed to violate everything known about astronomy since the original work of Copernicus, who found that there was nothing special about the location of the Earth in the universe. Second, one might abandon the ether theory and Newtonian mechanics along with it. So both of these choices were unpleasant because, well, by the way, we had, as a human race, we had actually faced a lot of obstacles in astronomy when we, proved that the Earth was not the center of the universe. That was a whole thing. That was a very difficult for people like Copernicus to prove to the world. It was very much opposed. So, this thing about the Earth moving and not being the center of the universe, the Earth actually moved around the sun. This was now accepted. So, this whole thing about the ether not affecting the speed of light might suggest that maybe the Earth is not moving, etc. That was very disturbing because we had just proved that, in fact, the Earth is moving. So, this was unpleasant. And the other thing was, well, Newtonian mechanics is the one from which extended the ether theory. And so maybe we have to get rid of the ether theory. Heroic efforts were made to salvage the ether theory. The closest step toward a resolution to this puzzle was found by the Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald. They reasoned that the Earth, in its motion through the ether, was actually physically compressed by the ether wind, so that all meter sticks in the Michelson-Morley experiment were shrunken. The ether, which already had near mystical properties of being invisible, non-compressible, extremely dense, and so on, now had one more property. It could mechanically compress atoms by passing through them. This would conveniently explain the negative result. In this picture, the speed of light did in fact change, but you could never measure it because every time you tried using a meter stick, the velocity of light would indeed change and the meter sticks would shrink in the direction of the ether wind by precisely the right amount. Wow, so they were really trying to make this ether theory work. So I should tell you that there is no ether. We are simply following sort of what transpired here to lead Einstein to work on this and come up with the resolution for all of this that we speak about today. And that was with the special theory of relativity. But you can see how all of these people trying to make it work with ether, even the things that they're talking about with the meter sticks and, things shrinking, one could see how this would all inspire him, fortunately, in the right direction, which is to think about relativity and the speed of light, which is formalized in his special theory of relativity. But all of these people and their efforts, even if they were misled or even if they were kind of wrong, still is helpful because it's helpful to study what is going on and to literature review the current state of affairs, to then take from it what you will and put it into your own work. Lorentz and Fitzgerald independently calculated the amount of shrinkage. Wow. Yielding what is now called the Lorentz-Fitzgerald contradiction. Neither Lorentz... Yeah, here we go. I can pet the cat. Here, he's a baby too. He's a baby. We'll be here for a while now, BJ, so no worries. Lorentz and Fitzgerald independently calculated the amount of shrinkage, yielding what is now called the Lorentz-Fitzgerald contraction. Neither Lorentz nor Fitzgerald were especially pleased with this result. It was simply a quick fix, a way of patching up Newtonian mechanics, but it was the best they could do. Not many physicists liked the Lorentz-Fitzgerald contraction either, since it smacked off being an ad hoc principle thrown in to prop up the sagging fortunes of the ether theory. So this is how basically the ether theory, because Newtonian mechanics suggested the ether theory, and because Newton was well respected and his mechanics, his work was understood for 2 centuries, we are seeing a level of struggle with basically updating his theory to be more correct. It required some level of failures and struggles and challenges to completely do away with the fact that there might be some basis in Newtonian mechanics, which is really about the absolute frame of reference, which had to be done away with and would usher in the concepts of relativity. But all of that struggle by other reputed scientists and experimentalists actually helped Einstein to do this. Hi, Deputy Warden Gallant. How are you? So hopefully it's becoming a little bit more clear as we talk about this more, Molly. But thank you for joining. So, to Einstein, the idea of the ether, with its near miraculous properties, seemed artificial and contrived. Earlier, Copernicus had destroyed the Earth centered solar system of Ptolemy, which required the planets to move in extremely complex circular motions called epicycles. So, right, I forgot to mention that, I was mentioning earlier that Copernicus had immense difficulty getting rid of the concept that the Earth was in the center of the universe. And even back then, to preserve that concept, people had worked very hard and had come up with a concept called epicycles, which would allow for this complicated setup to work. And so he had done away with epicycles. And now we know exactly what our orbits are like. Sun, the Earth is not the center of the solar system, the sun is, and each planet has a particular orbit around the sun. It's elliptical, in fact. All these complications like epicycles and things like that. I love cats. You're beautiful. Thank you. Hi, Molly. Thank you very much. Thank you for listening to the book. So, it's not the first time that people had overcomplicated matters in order for a theory to be preserved. So, Einstein might have thought of that as far as the ether goes. Ether theory was also a complicated theory trying to preserve something that may actually be wrong to some extent. It's not that Newtonian mechanics is always wrong or that it doesn't work, in classical setups, but it had its limitations, and it was time to update this whole thing. And that's what Einstein was going to do. So with Occam's razor, Copernicus sliced away the blizzard of epicycles needed to patch up the Ptolemaic system and put the sun at the center of the solar system. So Copernicus had been very brave when he put the sun at the center of the solar system, and it really made things make much more sense, and it also simplified things because at that time, just before Copernicus did that, they had a very complicated geometry for the solar system to make the way they thought work. Like Copernicus, Einstein would use Occam's razor to slice away the many pretensions of the ether theory. And he would do this by using a children's picture. Ooh, interesting. Thistle, hi. Hello, my friend. Hi, Thistle. Hi, Molly. Okay, Molly, tomorrow we meet again. Tomorrow we will live stream again, afternoon time here in Boston. Thank you for joining. So now we will get into the juicy part, which is chapter 3 of Einstein's Cosmos. We just read about the ether theory and all the challenges with it, and we also compared it to the sort of difficulties and complications in the epicycles and older solar system theory, which had to be done away with by Copernicus, who then showed that the sun was at the center of the solar system, not the Earth. So yeah, such big upheavals do happen in science, and it's exciting, and we are fortunate to be able to learn about them after the fact. Intrigued by Marx, so now we're starting chapter 3 of Special Relativity and the Miracle Year, and here is Baji and myself. Hi, Afshin. Hi. Such a cute kitty. Thank you so much. Thank you for joining. Thank you. Where are all my friends? BJ asked, maybe he'll come back. Hi, Big Chunga. Hi, Adventure Life Nova. Hi, BJ. Hi, Vic Boss. Hi, Valikika. Hi, Cam's Beats. You know BTS. I think so. Is that usually your username? My name is Lynn. Oh, hi, Lynn. Such a cute kitty. Thank you. Sorry, I do unfortunately have to go to bed early tonight because tomorrow will be a busy day, but thanks for the fun night. Have a good rest of your time. Bye. And I will be here tomorrow for longer. Oh, sure. Yeah, not your average cat. So, tomorrow we will be going live at a more regular hour for the United States time. We will be going live in the afternoon. So, on Saturday, Sunday, I go live Boston time afternoon. So, it's not like so late. Hi. Hi, P5NNC1T. How are you? Hi, Waygate Esther. I'm going to bed. Okay, Molly. Thank you, love. Thank you so much for joining. Oh, Molly. See you tomorrow. It's going to be great. We're going to have a nice live tomorrow in the afternoon. I'm watching. Are you sure it's a show on Disney from two of the BTS member? Hi, PF or hi, P5NN. Hi, P5NN. How are you? So we will definitely have a nice live tomorrow. So it won't be like so late. But I figure these late lives can be nice for the Asia people who are joining in the morning time for them. Bye. I'm gonna finish the show. Okay, bye. So, yeah, thank you so much, friends, for joining today. We will keep on reading for now, but we will be live for longer tomorrow in the afternoon time for United States. So, catch you then, but we'll keep going for a little bit longer here. Special Relativity and the Miracle Year. Intrigued by Mach's criticisms of Newton's theory, so Mach, remember, had criticized some of Newton's theories. He had said some things that may not have agreed with some people, or some of things may have agreed, or something like that. But at least he had sort of started to criticize and kind of question Newtonian mechanics, which seemed to be not working in some cases. So Einstein went back to the picture that had haunted him since he was 16, running alongside a light beam. Have a nice night. Love you, girl. Thank you. Christina says, I heard about that. Yes, I read it. And actually somebody in this live told me about that. So yeah, sorry to hear that news. Your cat is so cute. Thank you, P5NN. Thank you so much, P5NN. Thank you for joining. Bye, Lynn. I think Afshin told me that her name is actually Lynn. Love you too, girl. Thank you. Thank you so much. See you tomorrow, okay? Yeah, I know it got late for the well, today's Friday, right? But yeah, I understand. It's late for the US people right now. So if you have to go to bed, I understand. But we'll catch you in the afternoon tomorrow, Boston time. Or whatever time for you at that time. So yeah, thank you. So now Einstein is imagining running next to a light beam. So this concept of remember how Michelson and Morley were doing the experiment to see if there was ether, then depending on the movement, depending on the light beam that is either going with the ether direction or against it, they were expecting some results. But they saw that the speed of light was the same. There was no difference. And that led to a lot of confusion about even whether, the earth was moving or not. Because people thought, well, the ether wind should be different based on obviously the Earth's movement, if you're going with it or against it. And so it should do something to the speed of light, but they were getting confusing results. Einstein is now doing some thought experiments here in this chapter. I'm going to watch. I love cats. I'm going to watch more lives. Yes, we go live pretty regularly, but our most well watched, I think, lives are probably the Saturday, Sunday lives in the afternoon times, Boston time afternoon. So catch you then. Generally, we have really nice chats at that time. I mean, we've had really nice discussions whenever during the nights as well. But yeah, we get to see a lot of nice hangouts with the kitty cats on Saturday, Sunday afternoons. He returned to the curious but important discovery that he made while at the Polytechnic, that in Maxwell's theory, the speed of light was the same, no matter how you measured it. For years, he puzzled over how this could possibly happen, because in a Newtonian, common sense world, you can always catch up to a speeding object. Imagine again the police officer chasing after a speeding motorist. If he drives fast enough, the officer knows that he can catch up to the motorist. Anyone who has ever gotten a ticket for speeding knows that. But if we now replace the speeding motorist with a light beam, and an observer witnesses the whole thing, then the observer concludes that the officer is speeding just behind the light beam, traveling almost as fast as light. We are confident that the officer knows he's traveling neck and neck with the light beam, but later, when we interview him, we hear a strange tale. He claims that instead of riding alongside the light beam, as we just witnessed, it sped away from him, leaving him in the dust. He says that no matter how much he gunned his engines, the light beam sped away at precisely the same velocity. In fact, he swears that he could not even make a dent in catching up to the light beam. No matter how fast he traveled, the light beam traveled away from him at the speed of light, as if he were stationary instead of speeding in a police car. So you understand? Hi, JP. You understand Einstein's thought experiment and his sort of difficulty with the speed of light. Basically, Maxwell had found the speed of light, and he had basically found that the speed of light is the same no matter in what reference frame. So then, but from Newtonian mechanics, we knew something about, if two things were moving, if you increased your speed, you could catch up to the other object. So then Einstein is replacing one of the things with a light beam and thinking whether, can you catch up to the light beam? Can you, if one of the things is a police officer and the other, instead of a speeding motorist, is a light beam, can you catch up to it? That's the thought experiment here. So by thinking about these challenging things, we're actually going to make a lot of profound discoveries in this chapter. But when you insist that you saw the police officer speeding neck and neck with the light beam within a hair's breadth of catching up to it, he says you were crazy. He never even got close. To Einstein, this was the central nagging mystery. How was it possible for two people to see the same event in such totally different ways? So this is where relativity comes in. Newtonian mechanics would say that there is an absolute frame of reference and the one thing does catch up to the other. But in Einstein's thought experiment, what he's seeing, what he's thinking, is that actually there are two different stories depending on the observer. How was it possible for two people to see the same event in such totally different ways? What's the reason for owning pets? Well, cat lovers like cats. We love cats. That's the reason. And cats love us. If the speed of light was really, and it's kind of strange because it might be strange to think about that the two observers are seeing two different things happen, but when you put, it's almost like if the speed of light is a constant, no matter what, then those two different stories are actually both true. And that's where relativity, like literally what you see is relative, that's where that comes in from. So he basically took one truth, which is the speed of light, and derived a whole theory from it, and really drove home the fact that the speed of light is constant. So the speed of light being a constant has a ton of very interesting consequences, and that's what we cover here in this chapter. How was it possible for two people to see the same event in such totally different ways? If the speed of light was really a constant of nature, then how could a witness claim that the officer was neck and neck with the light beam? Yet, the officer swears that he never even got close. Einstein had realized earlier that the Newtonian picture, where velocities can be added and subtracted, and the Maxwellian picture, where the speed of light was a constant, were in total contradiction. Newtonian theory was a self-contained system resting on a few assumptions. If only one of these assumptions were changed, it would unravel the entire theory in the same way that a loose thread can unravel a sweater. That thread would be Einstein's daydream of racing a light beam. One day around May of 1905, Einstein went to visit his good friend Michel Bessot, who also worked at the patent office, and laid out the dimensions of the problem that had puzzled him for a decade. Using Bessot as his favorite sounding board for ideas, Einstein presented the issue. Newtonian mechanics and Maxwell's equations, the two pillars of physics, were incompatible. One or the other was wrong. Whichever theory proved to be correct, the final resolution would require a vast reorganization of all of physics. He went over and over the paradox of racing a light beam. Einstein would later recall the germ of the special relativity theory was already present in that paradox. They talked for hours, discussing every aspect of the problem, including Newton's concept of absolute space and time, which seemed to violate Maxwell's constancy of the speed of light. Eventually, totally exhausted, Einstein announced that he was defeated and would give up the entire quest. It was no use. He had failed. So it looks like he collaborated with Michel Bessot, because I should mention that when you're coming up with these theories and concepts, it's very important to collaborate and talk to people and think through things with another person. And it looks, Einstein didn't really do things in a vacuum, pun intended, right? He really did look at a lot of people, a lot of scientists and experimentalists' work and derive from their work what he came up with. And also he had collaborators. So I think in history it is easier to just give one person all the credit and to keep the story simple and say that, this one guy was really great and he did everything. And even though that might be true that he is great and he was great, but at the same time, generally it's a little bit more complicated than that. Generally people will derive a lot from other people's work, and of course the people that came before them, and all those publications and literature review is really the way forward in science. So, although Einstein was depressed, his thoughts were still churning in his mind when he returned home that night. In particular, he remembered riding in a streetcar in Bern and looking back at the famous clock tower that dominated the city. He then imagined what would happen if his streetcar raced away from the clock tower at the speed of light. He quickly realized that the clock would appear stopped. Since light could not catch up to the streetcar, but his own clock in the streetcar would beat normally. Oh my gosh. Oh, this is so juicy. He then imagined what would happen if his streetcar raced away from the clock tower at the speed of light. He quickly realized that the clock would appear stopped. Since light could not catch up to the streetcar, but his own clock in the streetcar would beat normally. Then it suddenly hit him. The key to the entire problem. Einstein recalled, a storm broke loose in my mind. The answer was simple and elegant. Time can beat at different rates throughout the universe, depending on how fast you moved. Imagine clocks scattered at different points in space, each one announcing a different time, each one ticking at a different rate. 1 second on Earth was not the same length as 1 second on the moon or 1 second on Jupiter. In fact, the faster you moved, the more time slowed down. Einstein once joked that in relativity theory, he placed a clock at every point in the universe, each one running at a different rate. But in real life, he didn't have enough money to buy even one. But that's the magic of physics and the magic of thought experiments. You can think up all the clocks you want, even if you cannot afford one. And at this point, Einstein was poor. This meant that events that were simultaneous in one frame were not necessarily simultaneous in another frame. As Newton thought, he had finally tapped into God's thoughts. He would recall excitedly, the solution came to me suddenly with the thought that our concepts and laws of space and time can only claim validity insofar as they stand in a clear relation to our experiences. By a revision of the concept of simultaneity into a more malleable form, I thus arrived at the theory of relativity. For example, remember that in the paradox of the speeding motorist, the police officer was traveling neck and neck with the speeding light beam, while the officer himself claimed that the light beam was speeding away from him at precisely the speed of light, no matter how much he gunned his engines. The only way to reconcile these two pictures is to have the brain of the officer slow down. Time slows down for the policeman. If we could have seen the officer's wristwatch from the roadside, we would have seen that it nearly stopped and that his facial expressions were frozen in time. Thus, from our point of view, we saw him speeding neck and neck with the light beam, but his clocks and his brain were nearly stopped. When we interviewed the officer later, we found that he perceived the light beam to be speeding away, only because his brain and clocks were running much slower. To complete his theory, Einstein also incorporated the Lorentz-Fitzgerald contraction. Except that it was space itself that was contracted, not the atoms, as Lorentz and Fitzgerald thought. The combined effect of space contraction and time dilation is today called the Lorentz transformation. So if you've taken a relativity class, you would have seen this, like the Lorentz transformation, contraction of space and time. Thus, he could dispense entirely. So it's worth mentioning that the Lorentz and Fitzgerald experiment that led to this concept of contraction of the atoms, when they were doing that experiment to, to see how the ether wind might be affecting the speed of light. Well, that all that theory and experiment did help Einstein to come up with this concept of the Lorentz transformation, which is space contraction and time dilation. So the fact that space and time can be relative, So he did use even that sort of concept. He drew on it. Thus, he could dispense entirely with the ether theory. So, again, to complete his theory, Einstein also incorporated the Lorentz-Fitzgerald contraction, except that it was space itself that was contracted, not the atoms, as Lorentz and Fitzgerald thought. The combined effect of space contraction and time dilation is today called the Lorentz transformation. Thus, he could dispense entirely with the ether theory. Summarizing the path that he took to relativity, he would write, "I owe more to Maxwell than to anyone." Of course, absolutely. So, basically, a lot of people summarize special theory of relativity as sort of the more elegantification of Maxwell's equations. Really, it falls out of Maxwell's equations because Maxwell had already shown that the speed of light was a constant, right? Because Maxwell's equations spat out the speed of light as a constant. And so once you accept that and you do these thought experiments that Einstein did, this whole relativity of space-time fell out of it because of the speed of light being a constant. So that's why a lot of people consider special theory of relativity sort of a reimagination of Maxwell's equations, and further sort of, Maxwell's equations being true leads to special theory of relativity. So of course he did owe a lot to Maxwell for this work, and that's why we give credit. And as I mentioned before, when we take the E&M classes, electricity and magnetism classes, whether in undergrad or grad, generally we start with Maxwell's equations. Physicists have to learn Maxwell's equations. I think that the notation of special relativity, because you have to be familiar with it anyway, in the end, might be a better idea to start the class with in grad school. I actually suggested that to my professor, so maybe some people do that because special relativity basically gives you all of that because it's the more updated concept, right? Anyway, apparently, although he was dimly aware of the Michelson-Morley experiment, the inspiration for relativity did not come from the ether wind, but directly from Maxwell's equations. The day after this revelation, Einstein went back to Besso's home and, without even saying hello, he blurted out, "Thank you, I've completely solved the problem." He would proudly recall, "An analysis of the concept of time was my solution. Time cannot be absolutely defined, and there is an inseparable relation between time and signal velocity." For the next 6 weeks, he furiously worked out every mathematical detail of his brilliant insight. Because that's what this is a brilliant insight. Because, Maxwell's equations had existed and no one had really interpreted them in the way that Einstein had. So that's why it's such an important, it's so important to be a good student of physics, because you don't want to just study physics. You want to study it so well and understand what has been done so far so well that you can even see the flaws in, where there are flaws, and you can see the truth in an even bigger truth way where there's truth. And so he saw the truth of speed of light being a constant in Maxwell's equations and extended that to be a whole theory of its own, which is a special theory of relativity. And that is called a brilliant insight, leading to a paper that is arguably one of the most important scientific papers of all time. According to his son, he then went straight to bed for 2 weeks after giving the paper to Mileva to check for any mathematical errors. Oh, so that was his wife. So again, he collaborated a lot, it seems, with women, but often those women are not really credited for their contributions, because I think in the old-fashioned old days, that was not the case where women were credited. Oh well, the final paper on the electrodynamics of moving bodies was scribbled on 31 handwritten pages, but it changed world history. So he wrote a 31-page paper on electrodynamics of moving bodies. Love it. In the paper, he does not acknowledge any other physicist. He only gives thanks to Michel Besso. Einstein was aware of Lorentz's early work on the subject, but not the Lorentz contraction itself, which Einstein found independently. It was finally published in Annalen der Physik in September 1905 in volume 17. In fact, Einstein would publish 3 of his path-breaking papers in that famous volume 17. His colleague Max Born has written volume 17 is one of the most remarkable volumes in the whole scientific literature. It contains 3 papers by Einstein, each dealing with a different subject and each today acknowledged to be a masterpiece. Oh, wow. Amazing. Copies of that famous volume recently sold for $15,000 at an auction in 1994. So, wow, yeah. So, Annalen der Physics in September 1905, volume 17, is where he published his path-breaking papers. With almost breathtaking sweep, Einstein began his paper by proclaiming that his theories worked not just for light, but were truths about the universe itself. Remarkably, he derived all his work from 2 simple postulates applying to inertial frames, that is, objects that move with constant velocity with respect to each other. The laws of physics are the same in all inertial frames. The speed of light is a constant in all inertial frames. Those are the 2 postulates. So there we go. That is what everything's going to fall out of. So all of his math is going to fall out of this. So let's read it again. Einstein began his paper by proclaiming that his theories worked not just for light, but were truths about the universe itself. Remarkably, he derived all his work from 2 simple postulates. This is the elegance of special theory of relativity. It's very simple in the sense of it's deep insight, but it's simple. See, 2 simple things written there. Laws of physics are the same in all inertial frames. Speed of light is a constant in all inertial frames. And what are inertial frames? Objects that move with constant velocity with respect to each other. These 2 deceptively simple principles mark the most profound insights into the nature of the universe since Newton's work. From them, one can derive an entirely new picture of space and time. First, in one masterful stroke, Einstein elegantly proved that if the speed of light was indeed a constant of nature, then the most general solution was the Lorentz transformation. He then showed that Maxwell's equations did indeed respect that principle. Last, he showed that velocities add in a peculiar way. Although Newton, observing the motion of sailing ships, concluded although Newton, observing the motion of sailing ships, concluded that velocities could add without limit, Einstein concluded that the speed of light was the ultimate velocity in the universe. Imagine for the moment that you're in a rocket speeding at 90% the speed of light away from Earth. Now fire a bullet inside the rocket that is also going at 90% the speed of light. According to Newtonian physics, the bullet should be going at 180% the speed of light, thus exceeding light velocity. But Einstein showed that because meter sticks are shortening and time is slowing down, the sum of these velocities is actually close to 99% the speed of light. In fact, Einstein could show that no matter how hard you tried, you could never boost yourself beyond the speed of light. Light velocity was the ultimate speed limit in the universe. Hi. Deputy says, you're so pretty, Harry single. Well, thanks, I guess. So light velocity was the ultimate speed limit in the universe. Hi, thank you for joining. We never see these bizarre distortions in our experience because we never travel near the speed of light. For everyday velocities, Newton's laws are perfectly fine. So this is what I've been also mentioning, which is that Newtonian mechanics worked so well because most of the time they do work very well. If you're not traveling close to the speed of light, or if you're not traveling very fast, or if you're, if you're not trying to make a very accurate measurement like GPS travel or something that uses, satellite communication and down to our cars. If you don't want something so precise, then Newton's laws work just fine. Newtonian mechanics held steady, held true for 200 years because it does work. Most of the time we can actually just do classical mechanics and everything is fine. And so, in for physicists, we do spend a year learning classical mechanics or Newtonian mechanics, and we spend another year doing that in grad school because Newtonian mechanics can also solve a lot of problems. And most of the time, that's all you need. A lot of engineering is based on Newtonian mechanics. So we must understand those well as well. But it just so happens that the more correct theory for light and understanding these mechanics and, to be consistent with E&M as described by Maxwell, you need the special theory of relativity. So keep in mind that things can still work even without special theory of relativity, but special theory of relativity is the more correct theory. So we never see these bizarre distortions in our experience because we never travel near the speed of light. For everyday velocities, Newton's laws are perfectly fine. This is the fundamental reason why it took over 200 years to discover the first correction to Newton's laws. But now imagine that the speed of light is only 20 miles per hour. If a car were to go down the street, it might look compressed in the direction of motion, being squeezed like an accordion down to perhaps 1 inch in length, for example, although its height would remain the same. Because the passengers in the car are compressed down to 1 inch, we might expect them to yell and scream as their bones are crushed. In fact, the passengers see nothing wrong, since everything inside the car, including the atoms in their bodies, is squeezed as well. As the car slows down to a stop, it would slowly expand from 1 inch to about 10 feet, and the passengers would walk out as if nothing happened. Who is really compressed, you or the car? According to relativity, you cannot tell, since the concept of length has no absolute meaning. So according to Einstein, please zoom out. I am zoomed out. Sorry. He's very close to me. Oh, I'm so sorry. Oh, very sorry, Tierney. So sorry, Tierney Page Poda. Extremely sorry. We don't have to. We can look at the blanket instead. So as the car slows down, so let's read about that again. As the car slows down to a stop, Baji has gone this way, but he was brown tiger striped. Yeah. I here to learn English speaking. Oh, hi Topicus. Hi Topicus, vlog. Hello, yes. Happy to help. Happy to help. Thank you. And sorry, Tierney. As the car slows down to a stop, it would slowly expand from 1 inch to about 10 feet, and the passengers would walk out as if nothing happened. Who is really compressed, you or the car? According to relativity, you cannot tell, since the concept of length has no absolute meaning. So in relativity, the concept of length itself is relative, and time is relative. the speed of light is constant, which renders time relative and length relative. So, with those in mind, we can do these thought experiments by even, imagining the speed of light to be less than the real speed of light, and, you know, thinking about how things might look if that was the case. In retrospect, one can see that others came tantalizingly close to discovering relativity. So, this is what we were saying earlier, is that a lot of people were doing these experiments and thinking about the contradictions between Newtonian mechanics and Maxwell's equations. And so, really, a lot of people could have discovered relativity themselves. It really took that brilliant insight of Einstein, though, to put it all together, which is really nice. And and also because he was such a good student of everybody else's work, that's why he was able to put it all together. So one can see that others came tantalizingly close to discovering relativity. Lorentz and Fitzgerald obtained the same contraction, but they had the totally wrong understanding of the result, thinking it was an electromechanical deformation of the atoms rather than a subtle transformation of space and time itself. Henri Poincaré, recognized as the greatest French mathematician of his time, came close. He understood that the speed of light must be a constant in all inertial frames, and even showed that Maxwell's equations retained the same form under a Lorentz transformation. However, he too refused to abandon the Newtonian framework of the ether, and thought that these distortions were strictly a phenomenon of electricity and magnetism. So he came close, but he did not want to abandon the whole Newtonian framework and ether stuff. Einstein then pushed further and made the next fateful leap. He wrote a small paper, almost a footnote, late in 1905, that would change world history. If meter sticks and clocks became distorted the faster you moved, then everything you can measure with meter sticks and clocks must also change, including matter and energy. In fact, matter and energy could change into each other. So this is where there's a big leap, So the meter sticks and clocks, or in other words, length and time being relative, was the first step. That's what fell out of light being a constant of nature, the speed of light being a constant of nature. But then he's also talking about, well, what do we measure with meter sticks and clocks? What else is relative? And he's saying that matter and energy could be relative, and those could even turn into each other. For example, Einstein could show that the mass of an object increased the faster it moved. Its mass would in fact become infinite if you had the speed of light, which is impossible, which proves the unattainability of the speed of light. This meant that the energy of motion was somehow being transformed into increasing the mass of the object. Thus, matter and energy are interchangeable. If you calculated precisely how much energy was being converted into mass, in a few simple lines, you could show that E equal to mc squared, the most celebrated equation of all time. So, this E equals to mc squared comes out of special relativity. Since the speed of light was a fantastically large number and its square was even larger, this meant that even a tiny amount of matter could release a fabulous amount of energy. A few teaspoons of matter, for example, has the energy of several hydrogen bombs. In fact, a piece of matter the size of a house might be enough to crack the earth in half. Einstein's formula was not simply an academic exercise, because he believed that it might explain a curious fact discovered by Marie Curie. So remember, we talked about Marie Curie's radioactivity work, and that had also given some trouble to Newtonian mechanics and sort of conservation of energy, because Newtonian mechanics said that energy, laws of conservation of energy, but she was demonstrating radioactivity and things like that. And so this E equals to mc squared was needed to explain Marie Curie's work as well. fact discovered by Marie Curie that just an ounce of radium emitted 4,000 calories of heat per hour indefinitely, seemingly violating the first law of thermodynamics, which states that the total amount of energy is always constant or conserved. He concluded that there should be a slight decrease in its mass as radium radiated away energy. Hi, Baji Baba. He concluded that there should be a slight decrease in its mass as radium radiated away energy, an amount too small to be measured using the equipment of 1905. The idea is amusing and enticing, but whether the Almighty is laughing at it and is leading me up the garden path, that I cannot know, he wrote. He concluded that a direct verification of his conjecture, for the time being, probably lies beyond the realm of possible experience. Why hadn't this untapped energy been noticed before? He compared this to a fabulously rich man who kept his wealth secret by never spending a cent. Did you know we can slow down the speed? No, I did not know that. I don't believe that's true. Banish Hoffman, a former student, or are you talking about like gravitational lensing, where a very massive body can make light bend? That would be something different. Banish Hoffman, a former student, wrote, "Imagine the audacity of such a step. Every clod of earth, every feather, every speck of dust becoming a prodigious reservoir of untapped energy." There was no way of verifying this at the time, yet in presenting his equation in 1907, Einstein spoke of it as the most important consequence of his theory of relativity. So, he didn't think probably in the beginning when he was working on special theory of relativity with the length contraction and the time dilation and the speed of light being a constant, he probably didn't think that it would lead to this energy and mass relation. So that is also to be noted, that sometimes we go down a path and we might actually discover something that we did not expect. It might actually have a different conclusion than you might expect. So this mass energy work that it led to with his special theory of relativity is not something that he expected. And indeed, it had some other applications that he might not have expected or liked. His extraordinary ability to see far ahead is shown by the fact that his equation was not verified until some 25 years later. So this is quite common with Einstein's work, where he is I'm reading this book called Einstein's Cosmos by Michio Kaku. All right, so some of the things that he discovered were not really confirmed until years later, but they were confirmed, which is nice. Once again, the relativity principle forced a major revision in classical physics. Before, physicists believed in the conservation of energy. So this is what I was saying. With the whole mass energy conversion, he also corrected a previously Newtonian concept, which is the conservation of energy. Also, the first law of thermodynamics, which states that the total amount of energy can never be created or destroyed. Now, physicists consider the total combined amount of matter and energy as being conserved. Einstein's restless mind tackled yet another problem that same year, the photoelectric effect. Henrik Hertz, back in 1887, noticed that if a light beam struck a metal, under certain circumstances, a small electric current could be created. This is the same principle that underlies much of modern electronics. Thank you. Thank you, Yosin. Thank you, Yosin. Solar cells convert ordinary sunlight into electrical power, which can be used to energize our calculators. TV cameras take light beams from the subject and convert them into electric currents, which eventually wind up on our TV screen. However, at the turn of the century, this was still a total mystery. So, photoelectric effect is what we're talking about now. Hi, Yosin. Hi, BG. That's what he actually got his Nobel Prize for. So even though his theory of relativity is so famous and that's what he's more known for, but his contribution to photoelectric effect is actually how he got the Nobel Prize. Anyway, we'll read about this just now. At the turn of the century, this was still a total mystery. So like the whole solar cell thing, actually in Massachusetts, solar panels are quite common. Because of our high energy bills, sometimes the state will even pay for your solar panels on your roofs so that you can convert solar energy into little electrons that can give you electricity. And that is called the photoelectric effect. And Einstein worked on that. So we have him to thank for that. We have some other people to thank for that. I personally do not have solar panels yet, but they are very common here. If you go around the different neighborhoods of Massachusetts, you will see a lot of the houses actually have a bunch of solar panels on their roofs. This was still a total mystery at the turn of the century, which is early 1900s is what we're talking about. So in the early 1900s, when he won the Nobel Prize, that's what he got it for, actually. Yeah, I'm trying to see if there's a year here somewhere, but early 1900s, this was still not known. Somehow the light beam was knocking electrons out of a metal, but how? So light beam can knock electrons out of the metal. This is what they were suggesting, the scientists, right? Because Heinrich Hertz had experimentally noticed that, and Einstein also talked about his mass energy conversion with his relativity theory. So, yeah, Newton had believed that light consisted of tiny particles that he called corpuscles. So this is very interesting because remember, Newton himself had done some optics work and he had already come up with this concept of the tiny particles that light may be made up of called corpuscles. But physicists were convinced that light was a wave, and according to classical wave theory, its energy was independent of its frequency. For example, although red and green light have different frequencies, they should have the same energy, and hence, when they hit a piece of metal, the energy of the ejected electrons should be the same as well. Similarly, classical wave theory said that if one turned up the intensity of the light beam by adding more lamps, then the energy of the ejected electrons should increase. The work of Philip Leonard, however, demonstrated that the energy of the ejected electrons was strictly dependent on the frequency or color of the light beam, not its intensity, which was opposite the prediction of the wave theory. So wave theory said it should be the intensity of light that gives the energy of the electron, but this said that Philip Leonard demonstrated that it was not the intensity of light, but the frequency of light or the color of light that contributed to the energy. Einstein sought to explain the photoelectric effect by using the new quantum theory recently discovered by Max Planck in Berlin in 1900. So again, he's being a good student of all the other physics and discoveries being made in his contemporary times, which is very important. So Max Planck had come up with his quantum theory during those days as well. And so Max Planck had his quantum theory, which probably people were not taking very seriously at that time. Planck made one of the most radical departures from classical physics by assuming that energy was not a smooth quantity like a liquid, but occurred in definite, discrete packets called quanta. The energy of each quantum was proportional to its frequency. This is quite this is quite profound. This is not something that anybody, this is not classical at all. The classical mechanics that we knew had nothing to do with this quanta stuff, right? So that's why we have classical mechanics and we have quantum mechanics. Again, classical mechanics is taught in a year, and quantum mechanics is taught in a different year. Different fields of physics. So this is again very, very profound that Max Planck did this in 1900, and soon after Einstein was going to leverage this work as well, which is very important to leverage other people's good work. The energy of each quantum was proportional to its frequency. The proportionality constant was a new constant of nature, now called Planck's constant. One reason why the world of the atom and the quantum seems so bizarre is the fact that Planck's constant is a very small number. Einstein reasoned that if energy occurred in discrete packets, then light itself must be quantized. So this was also profound because, even though Newton had talked about light being corpuscles, this whole concept of light being quantized, because remember, we've done all this work, all of the Maxwell's equations, all of this, everything that we've learned about so far, giving light wave nature, does not talk about light being quantized or light being particles. And this is where the wave-particle duality of light comes in. And he was inspired by Planck's work, who had basically given birth to quantum mechanics, Planck. So anyway, Einstein's packet of light quanta was later christened the photon, a particle of light, by chemist Gilbert Lewis in 1926. So I suppose light was not called a photon until 1926. Einstein reasoned that if the energy of the photon was proportional to its frequency, then the energy of the ejected electron should also be proportional to its frequency, contrary to classical physics. Because again, classical physics would consider intensity of light to have played a role in the intensity of the electron that was ejected. And the fact that metals, when solar light fell on metal, can eject an electron, that was already being shown experimentally, remember. So it's not like Einstein, saw that happen himself. He leveraged somebody else measuring that to happen. So that's, again, very important to keep up with everybody else's, not everybody else, but, the work that is happening, that is also progressing science. And now, basically the photoelectric effect, the importance of understanding it is what Einstein is credited for, because people had measured the electron being coming out of the metal that on which sunlight had fallen, but exactly how the energy of the electron was, related to the sunlight energy or frequency or whatever, lights, because sunlight is sunlight, but what if I chose to put just some kind of red light on the metal, right? How would that change the energy of the electron that was emitted? This type of math is what Einstein came up with his photoelectric effect. And that is where he leveraged Max Planck's work with the concept of the quanta, where packets of energy, it was proportional to the frequency of light. So Einstein's new picture, a quantum theory of light, made a direct prediction that could be tested experimentally. So this is the great strength also, is that if you predict something that can be tested experimentally readily, then all the more reason for success. It's very difficult to theorize about things that are difficult to test out experimentally, because then if your theory cannot be, tested, then it might not be recognized as a correct theory. By turning up the frequency of the incoming light beam, one should be able to measure a smooth rise in the voltage generated in the metal. This historic paper, which would eventually win him the Nobel Prize in Physics, was published on June 9, 1905, with the title On a Heuristic Point of View Concerning the Production and Transformation of Light. With it, the photon was born, as well as the quantum theory of light. Amazing. Wow. This is just incredible. So, do you see how he brought together so many things? There's a special theory of relativity, which has to do with length contraction, time dilation, the relative nature of space and time, leveraging the fact that speed of light is constant. Then from there, he goes to mass energy conversion and the relativity of mass and energy, where they could convert to each other, E equals to mc squared. And then he also leveraged Max Planck's work, which talked about quantas of energy, where energy is coming in packets and the energy of something is proportional to its frequency. Oh, I guess their food has decided to fall at this time. I wonder if it's gonna work. This, oh God. I hope it stops. Okay, yeah. The auto feeder has been struggling. So I am just wondering. Okay, let me actually help out Fuji with his share of this. Hi babies, you have to share. I cannot believe that the auto feeder has worked out. And you have to share with Suji. Let me read about that quanta thing again. It's so juicy. Because of what Planck had suggested in 1900, it really helped Einstein with his photoelectric effect. Planck made one of the most radical departures from classical physics by assuming that energy was not a smooth quantity like a liquid, but occurred in definite, discrete packets called quanta. The energy of each quantum was proportional to its frequency. This is what he used also with photons, saying that if light was made up of quanta or photons, then that light quanta's energy depended on its frequency. And if that was the case, and you put light on metal and you get an electric current out of that, and if you changed the frequency of light that you used, you should see the voltage change. In other words, the energy that you get out change, and that would prove his theory. And because it was easily provable, easily demonstrated with experiment, that's why it was very successful, and he got the Nobel Prize for it in 1905. And remember, he wasn't very rich or had a stable job up till this point, so this is quite a big deal for him. This is quite a big deal for him. We're reading this book. So this is actually tremendous. And the paper name that he wrote on this, that won him the Nobel Prize, by the way, on photoelectric effect, is called On a Heuristic Point of View Concerning the Production and Transformation of Light. With it, the photon was born, as well as the quantum theory of light. So he also worked on the quantum theory of light. Like, I mean, come on, how productive. First, he did special theory of relativity, then the mass energy conversion. Now he has got the quantum theory of light and the photoelectric effect, which is, of course, also has a lot of direct application, which most people are interested in, is application. And that's why it was so well recognized. And he even got the Nobel Prize for it, which is a huge deal. His other work was probably less understood and not as appreciated, but this one was successful. In yet another article written during the miracle year of 1905. So 1905 is just an amazing year. You know, everything just went right during this year, apparently. Einstein tackled the problem of the atom. Although the atomic theory was remarkably successful in determining the properties of gases and chemical reactions, there was no direct proof of their existence, as Mach and other critics were fond of pointing out. Einstein reasoned that one might be able to prove the existence of atoms by noticing their effect on small particles in a liquid. Ah, that's right. That's right, Brownian motion. Brownian motion, for example, refers to tiny random motions of small particles suspended in a liquid. This property was discovered in 1828, so a lot earlier, by the botanist Robert Brown, who observed tiny pollen grains under a microscope exhibiting strange random motions. At first, he thought that these zigzag movements were like the motion of male sperm cells, but he found that this strange aberrant behavior was also exhibited by tiny grains of glass and granite. Goodness. Some had speculated that Brownian motion might be due to the random impacts of molecules, but no one could formulate a reasonable theory of this. Einstein, however, took the next decisive step. He reasoned that although atoms were too small to be observed, one could estimate their size and behavior by calculating their cumulative impact on large objects. If one seriously believed in the theory of atoms, then the atomic theory should be able to calculate the physical dimensions of atoms by analyzing Brownian motion. By assuming that the random collisions of trillions upon trillions of molecules of water were causing random motions of a dust particle, he was able to compute the size and weight of atoms, thereby giving experimental evidence of the existence of atoms. It was nothing short of amazing that by peering into a simple microscope, Einstein could calculate that a gram of hydrogen contained 3.03 times 10 to the 23 atoms, which is close to the correct value. The title was On the Movement of Small Particles Suspended in Stationary Liquids, required by the molecular kinetic theory of heat. That was in July that he did that. This simple paper, in effect, gave the first experimental proof of the existence of atoms. So that's very important, of course, as well. Ironically, just a year after Einstein calculated the size of atoms, the physicist Ludwig Boltzmann, who had pioneered the theory of atoms, committed suicide. Oh no. In part because of the incessant ridicule he received for advancing the atomic theory. Oh gosh. Oh, that's terrible. Boltzmann is very important. We all know about Boltzmann's constant. Oh, I didn't realize he committed suicide. Oh, shit. Oh, so sorry about that. I'm so sorry that he committed suicide. I forgot about that. After Einstein wrote these 4 historic papers, so, the relativity papers, photoelectric effect, so like the relativity papers have to do with the length and time dilation, speed of light constant paper, the mass energy conversion paper, the photoelectric effect paper, and the atomic size paper. Quite productive, I must say. After Einstein wrote these 4 historic papers, he also submitted an earlier paper of his on the size of molecules to his advisor, Professor Alfred Kleiner, as his dissertation. That night, he got drunk with Mileva. Oh, God. Oh, that's so funny. Oh, that's so funny. Hi, Tori. At first, his dissertation was refused, but on January 15th, 1906, Einstein was finally granted a PhD from the University of Zurich. So wait a minute. He didn't have his PhD before he had his Nobel Prize. Wow. Great. That's just great. Tells you everything about academia. He did not have his PhD, but he had a Nobel Prize. He could now call himself Dr. Einstein. The birth of the new physics. Oh, hi. Suji is having zoomies. She almost moved close to the speed of light here right now, and reached to the top of the room. Okay. So anyway, the birth of the new physics all took place at the Einstein residence on Crumgrass 49 in Bern. Today it is called the Einstein House. As you gaze through its beautiful bay window facing the street, you can read a plaque which states that through this window the theory of relativity was created. On the other wall, you can see a picture of the atomic bomb. Thus, 1905 was truly an annus mirabilis in the history of science, a miracle year. If we are to find another comparable miracle year, we would have to look back to 1666 when Isaac Newton, 23 years old, hit upon the universal law of gravitation. Hello. The integral and differential calculus, the binomial theorem, and his theory of color. So by the way, Newton had been very productive as well. In the year 1666, he came up with the universal law of gravitation, the integral and differential calculus, because also remember, Newton invented calculus, the binomial theorem, again, another very important theorem. So Newton did a lot of math in his Principia and his theory of color. So not bad for Newton either in 1666. In fact, Newton was very, very productive in his time. Einstein had finished the year 1905 laying down the photon theory, providing evidence for the existence of atoms, and toppling the framework of Newtonian physics, each of them worthy of international acclaim. He was disappointed, however, in the deafening silence that ensued. His work, it seemed, was totally ignored. Disheartened, Einstein went about his personal life, raising his child and toiling by himself at the patent office. Perhaps the thought of pioneering new worlds in physics was all a pipe dream. Yeah, I think a lot of people didn't really understand his work. Even now, to be honest, a lot of people don't understand his work. So can you imagine when he worked on all this back in the day, in 1905, 1906, people were probably still kind of adjusting to like whatever was happening then. Most people could not understand the enormity of his contributions. Most people indeed did not understand what he did, what he contributed. So it must have been a very lonely time. I could see that. It's very lonely. Lonely, lonely, lonely. What time is it? 2 in the morning? Place this here. Take a sip of my drink. This has been fun to read this, though. We're still in chapter 3. It's always lonely to be so intelligent and also so productive. It's like you produce so much work, but if there's not enough people to, or enough, human power to review your work, then that can be an issue, I think this is something about productive people. They create so much, but, there's not enough, people can't review it. You need to be smart to review it. Also, you need time to review it. It needs to be absorbed slowly. So you could do a lot of things being productive, but none of it is appreciated as much as it should be, Being productive has a flip side. Actually, give me a second. I'm going to go turn on the cat genie. You can look at Baji in the meantime. Hi, Suji. nose. Hi, Tori. Hi, BJ. Hi, Yasin. Yeah, I was thinking about being productive and how that can actually be quite painful for the person who is productive. Ah, my gosh. Anyways, oh well. I was gonna say, Planck must have been happy with him. In early 1906, however, the first glimmer of response riveted Einstein's attention. He got just a single letter, but it was from perhaps the most important physicist of the time, Max Planck, who immediately understood the radical implications of Einstein's work. What drew Planck to the theory of relativity was that it elevated a quantity, the speed of light, into a fundamental constant of nature. Yes. Planck's constant, for example, demarcated the classical world from the subatomic world of the quantum. And it's not a small thing to come up with a fundamental constant of nature, right? Even Planck's constant is daring. To say that the math works out for me to have this constant and like here it is, that's not easy. So Planck was something, someone really important. Jesus Christ. Please don't do this, Fuji. Please, can you move? Okay. So, to hear from Planck was a really big deal. Similarly felt Planck, Einstein was raising the speed of light into a new constant of nature. We were shielded from the equally bizarre world of cosmic physics by the huge value of the speed of light. So it's interesting because Planck's constant is small, but shielded from the equally bizarre world of cosmic physics by the huge... Right, because cosmic physics is where special relativity would be at play, in the universe. Universe is big, speed of light from our stars, from the stars in the sky, at those scales, cosmic physics is where, speed of light was relevant. But just like quantum world is bizarre and small, the cosmic world is also bizarre and small, and we're shielded from it with the huge value of the speed of light, which is so nice. It's a good thing we don't travel at the speed of light, or that the speed of light is so big. The speed of light is so big that basically classical mechanics worked for us for the longest time. And even now, classical mechanics or Newtonian mechanics works for the most part because the speed of light is very big. Where it would matter is at cosmic scales in the universe. But the universe is very interesting, and the closer we get to understanding it, the better. But it's almost like we've been shielded from quantum mechanics because we don't live at those tiny scales of quantum mechanics. And we've been shielded from special theory of relativity because we don't also live in cosmic scales either. We live in the scale of Newtonian mechanics and classical mechanics. And so our everyday life is made sense of with Newtonian mechanics, classical mechanics, and thermodynamics. So anyways, physicists learn that for a year in undergrad and grad because of that reason. But we also learn E&M, and we also learn quantum mechanics. I think classical mechanics is learned in the second year, E&M in the third year, and quantum in the senior year. So, and then they're learned again at the grad level in graduate school. So those are the big topics, and then there are more special topics like specifics like astrophysics, particle astrophysics, or particle physics. Those are all even more specialized courses that can be taken if you want to go into that in grad school or even in undergrad. But that's what it is. In this channel, we will talk about all these topics, I thought we'll start with a book like this because it can really help to set the tone of these different theories and how they were obtained, and also gives a historical sense of these discoveries. You know, it's important to understand that he started from Newtonian mechanics and all these different people's work and James Maxwell's equations, and speed of light being a constant fell out of that, and then all these other troubles led to the special theory of relativity. Understanding relativity is very important, and also the more easier concept to understand before we go into general theory of relativity, which is the more complete theory for gravitation. And also this intermingling with quantum mechanics is nice because that's how we got to photoelectric effect. And quantum mechanics itself is a world of its own, as we can see here with Max Planck being a sort of a father of it. Pretty sure he's called the father of quantum mechanics, unless I'm wrong. So we can also learn about that. In this book, I don't think a lot of quantum is covered, but we can also cover quantum in the channel because that's also a very interesting topic. So I think we'll pick up from page 46, this is still chapter 3, because I think we want to keep on talking about this and understand special theory of relativity even more next time, and see, we will finish this part and we'll go into part 2, which is the second picture, warped space-time. So I think the more we absorb the concept of special theory of relativity, the more comfortable we will be to tackle the general theory of relativity. And both of these are important to understand before we talk about the grand unified theory, which was actually incomplete and is still incomplete, and something that we might want to work on and further understand the state of affairs where we stand today in the world of physics. So that's why I think it's good to cover these topics. Cats give positive energy to humans. Of course. Yes. Thank you, Heike. Thank you for being here. It says it's 222 on my microwave. Good morning to Finland, England, Iceland, Japan, India, Pakistan, Sri Lanka, everywhere in Asia, I think. And actually, I don't know too much about what time is it in Africa right now. Australia, New Zealand, Antarctica, everybody, thank you so much for joining. Thank you for listening to the live replay video later on once it gets uploaded. I will see you again all tomorrow. We will go live at our regular Boston afternoon time, Saturday, Sunday. Hi, Fuji. Fuji was giving some trouble with the auto feeder. Hopefully it's working again. Thank you for being here and for enjoying Einstein's Cosmos by Michio Kaku. Thank you so much. Oh, Fuji's playing. Oh, good. Fuji Baba, kelbe. Africa is about the same time as Europe. Okay, good. Thank you. I was thinking because, yes, there's a lot of travel between Italy and Egypt. Egypt is Africa. It's like directly below. So yeah, you're right. I'm stupid. Africa has to be very similar to Europe because time has to do with the longitudes and longitudinally, I guess. But Africa's very big. I'm just thinking about the width of it because Europe is very small. Are parts of Africa... No, yeah, you're right. Those parts should be even more ahead. Yeah, okay. I just need to know. I just need to learn more about Africa because I've never been. Africa's huge and I've never been, so I need to learn more about Africa. But you're right. It's below Europe and Asia and that way. So yes, good morning also to Africa. Thank you. Yeah. Yep. we are in the nighttime over here in the United States of America because we are across the ocean over in this direction. Ah, beautiful place. Really? Oh, that's awesome. You have to tell me about Africa next time, Heike. What about? I need to. So the other day I met somebody from Eritrea, and I didn't even know about this country, and it's next to apparently Ethiopia, and they're very culturally similar. So as I meet people, then I learn about their country sometimes. In real life, I actually met somebody from Eritrea at my gym. So thank you to the gym. We are all from Africa. That is very true. We are all from Africa. Indeed. Indeed. So true. That's true. We've all been there because we're from there. Yes, absolutely. Hi, Baji. Anyway, thank you so much. Please do come to our live stream tomorrow at the regular time, afternoon time, okay? And we will continue. I'm going to think about it. I might continue either this book or I might start a new one, another murder mystery. But I might just continue this one. I'll think about it. I have a few book options, so I'll think about it. I think this one is pretty interesting, but I could also see how some people might not be interested in physics, but I think it's a very interesting topic. And it's also important culturally, I think. It's a cultural understanding. So if people are okay with it, I'm going to continue this tomorrow and Sunday at our usual live stream live time. And we will see you there. Thank you for all your contributions today. Really appreciate everybody listening and chatting and commenting. So yeah, thank you.